Hello, everyone. Thank you very much for listening to this talk. My name is Jordan Alexis Caraballo-Vega, and I work for the Science Data Processing Branch at the NASA Goddard Space Flight Center. I'm currently providing support to the NASA Center for Climate Simulation. And today I'm going to be talking about some of the work we have been doing with GPUs, particularly accelerating Earth science imagery processing. A bit about me. I'm an HPC and AML computer engineer. Mostly work on the AML side of Earth science applications, particularly working with GPU programming. The outline of this work, we're gonna first talk about some of the motivation and challenges that would lead to this project, some of the examples and use cases of the software, and then some of the AML use cases. The motivation is very clear, right? Earth science data holdings are just growing at exponential rate. We're just facing a fast-moving big data problem that we need to solve. And modern era hardware resources, particularly accelerated hardware like GPUs and TPUs, they have proven to be capable of processing this vast amount of data. And particularly when we combine them with AML techniques, we have a strong methodology to overcome some of these challenges. Now, the fact that we have both of them, both AML and particularly like accelerated hardware, we have additional problems and challenges. The fact that now our infrastructure becomes more complex, our interdependencies become bigger and even more complex. Then the fact that sometimes we develop software that works on-prem, but then doesn't actually work on the cloud. So we need to take into consideration developing code and software for both places. And then last but not least is the fact that now that we have many satellites and constellation of satellites, many of these files are just bigger than memory and bigger than the resources that we have. So we need to take into account what techniques and what storage devices we utilize to best use some of these bigger than memory file sets and how we can process them in parallel. So that's kind of the genesis of TerraGPU. And in TerraGPU, it's kind of a library that we've developed. It's just like we're developing so many projects leveraging some of the same techniques. Now we find out that some of the Earth science data structure, they greatly benefit from GPU acceleration. And we have many projects that we're using kind of like small chunks of them. But then we kind of want, like, we need to combine some of these libraries and we need to combine some of these techniques so we can use them elsewhere. And the main idea of this library, which is written in Python, is that we're going to leverage state-of-the-art high-performance computing software behind really organic and simple interface. So someone that doesn't, is kind of not familiar with GPU programming or even parallel programming, doesn't need to know what is on the back end. They just need to know how to access the data and how to like normally read geospatial data. And last but not least, one of the main things that we have been encountering when dealing with dependencies across different HPC clusters is that many of these software couldn't even run within the clusters. So we are now providing a container and Anaconda environments to actually provide additional reproducibility so we can share code across different HPC clusters. Some of the capabilities of this library, we support both rasters and vector-like data objects. So we're talking about geotiffs, shapefiles, and others. One of the main things is the calculation and processing of remote sensing indices. This is particularly useful when we're developing AML software that might require additional indices for segmentation or other applications. We process bigger than memory data sets, so there's no problem with having few resources for them processing bigger than the memory you have available. We have access to raw and georeference data manipulation. So we use GIRO and some of the wrappers like Rasterio and RioXArray for array manipulation. And then complete support of the AML development pipelines. So we have complete support for PyTorch and PyTorch Lightning. So we move and transfer data between what TerraGPU provides and then PyTorch and PyTorch Lightning. How the engine looks like? Well, it's kind of back end is DAS plus Numba, DAS at least for the scheduling, of CPU and multi-GPU resources and multi-node. And then we have NVIDIA OpenUCX for the actual networking communications and the intranode communications. And then NVIDIA Rapids, which is kind of the entire framework for the GPU libraries. It's kind of on top of all of these. And that is the one that manages most of the array-like and vector-like objects. But then the entire library is just array and vector agnostic. So you could use NumPy, QPy, or any other object that has the array function built in. And some of the, let's say, top layers of the infrastructure is Stereo, Xarray, and DuxArray, plus PyTorch and QML, which is another NVIDIA Rapids library for machine learning computations. And the main idea of TerraGPU is, first of all, we want to kind of have this interface that is just easy to use, a couple of lines of codes. And then on the long run, we want to have kind of this user interface of Jupyter notebooks where users do not even need to code. They can just provide some of their changes and some of the implementations via just moving widgets on the Jupyter notebook. Portability, I already discussed this, but the main idea is that we provide containers with several NVIDIA GPU CUDA libraries. So depending on the actual CUDA version that might be running on different clusters and MPI, we provide several versions of them. So we could kind of replicate across several HPC environments. Some of the computational resources that we have been using for testing the software, they have been from the NASA Center for Climate Simulation, particularly the Discover supercomputing cluster and the Prism GPU cluster. Prism in particular has 22 nodes, each one of them with 4 NVIDIA V100 GPUs. They do have a DGX node that has 8 A100 GPUs that we are probably doing benchmarking soon. And then on the CPU side, which sometimes is just important for kind of a comparison between GPU and CPU performance, each node has 20 cores of dual Intel 7 Cascade. The container environments were tested both on-prem and on AWS EC2 instances. One of the long-run, probably like in the next release, is testing the TerraGPU infrastructure on DAS Hub, which is one of the science-managed cloud environments provided by Sisto and Goddard. So that's one of the things that is coming along the lines. One of the examples, and this is just a simple example for calculating indices on a GeoTIFF. Note that we only have 3 lines of code in there. First, we read the data. This data in particular has 60,000 pixels on Y and then 11,000 pixels on X. This is a 1 meter resolution data. We then calculate the indices. We are calculating DVI, SI, and FDI, and then we save the actual calculations on there. Note how the DAS view in there shows that this is a data array, and then it's only consuming 22 gigs of memory. Know that this is kind of how the output would look like for a DVI index in a Ethiopia project that we're working on. And some of the benchmarking numbers, you can see that for the CPU would be 123 seconds to at least get to save the raster that we generated. We see around 16 bands, and then 65 seconds for a 4 GPU DAS backend process to finish. So we do have a big speed up. And just to kind of provide more insight, like imagine having to process 1,000 files of this, how much time you're actually saving with this effort. One of the AML use cases is kind of the random forest. The main idea is to just make it easier for, like, let's say, first run experiments. Know that you can initialize a random forest object with just 2 lines of code. First object is you need to specify where the data is located. Let's say that you have training and labels segregated in different files, and then the number of classes and the number of points you want to generate for your data set. In the case where you have already your CSV data set with the points that you want to train on, then you would just need to specify the number of classes and then the CSV file. But then all of the pipeline steps, let's say pre-processing, training, inference, they would all happen by those 2 lines of code. Another benchmarking numbers, like in simple scikit-learn, we'll have like 40 minutes if this was being done on CPU for a 47,000 by 39,000 pixel image. And then with TerraGPU on CPU only, just doing the DAS parallelization would be on 8 minutes inference. And then by using 4 GPUs on the back end, it will be 4 minutes inference. So there is a speed up in here that it becomes really useful when we're dealing with big numbers of data sets or big regions of very high resolution imagery. The second AML use case is CNN segmentation. We particularly have several networks that we can implement by doing PyTorch Lightning. This one in particular is a unit model that we're using for classifying and characterizing clouds in very high resolution imagery. Before this implementation, we would do inference of really large images that would take probably like hours on CPU, and then we started leveraging some of the GPU capabilities and then starting lowering down to minutes. But now we kind of reached that point where these bigger files, we only take 5 minutes of inference by doing multi-GPU on the back end via TerraGPU. There are limitations. Some of those limitations right now that we're dealing and working with is that there is no built-in GeoTIFF GPU reader. This makes it hard because we need them to offload between host and device memory from now and then, and it just takes time to actually, let's say, offload that memory into between CPU and GPU and then save into file. We're currently developing code to fix this. We're actually trying to write a driver to fix this issue so we could just offload between GPU and DAS and not need to actually move anything to the CPU. Getting the software, feel free to download the software, feel free to ask for additional implementation or enhancements. We're always open to add additions to the library. We mostly add additions based on some of the projects that come in and we get requests. So feel free to add anything or to use the code, including the Docker images for development. On the future release, which is coming on January, we're exploring QNumeric. It's one of those NVIDIA libraries that came in from the latest GTC, where they provide additional multi-node and multi-GPU capabilities. And we're testing that one with the new release. We also want to test DAS Hub on AWS, and then integrate additional Python Lightning CLI features that now it's going to actual production, so we can use some of those simplistic CLI options to then train additional models and increase the number of experiments you can run with by just changing and tweaking a couple of commands. Just as a recap, we really need to leverage accelerated hardware to keep the massive amounts of earth science data, and there's no way we can keep up with that if we don't provide accelerated software to take care of this, particularly GPUs and CPU parallelization. And then AML pipelines via TerraGPU can be easily initialized. They're just intuitively, and you just have a couple of line of codes to start working. And last but not least, we provide container environments with the precompiled dependencies. And not only for using TerraGPU, but just as a standalone, let's say, Earth Science container that you can leverage on applications via these containers. Some of the acknowledgements, and we thank everyone that has provided support to this project, particularly NCCS Computational Resources and the CISTA office. And thank you very much.